Defects in the bone and dura cause cerebral spinal fluid leaks into the mastoid cavity. These defects require a surgical procedure to repair. The surgeon must elevate the dura off the bone in order to insert a graft between the two layers, thereby patching the defect and stopping the leak. Due to the very limited space to work in and the pressure from the brain and cerebral spinal fluid that continually push the dura back down to the bone, this step of the procedure is prone to complications. Our team has developed multiple concepts in order to address these obstacles. This brings us to our first concept. Here we have a tool with a shepherd's crook-like tip that is able to rotate 360 degrees. The distal part of the tool is also angled so that the tip can fit into the mastoid cavity and enter the defect perpendicular to the bone. The shepherd's crook tip will be made out of a flexible material and have a cat tongue-like texture to aid in manipulation of the graft. There will be various angles of curvature and various sizes of the tips that are interchangeable to enable easier access to defects of various sizes and locations. Tactile feedback was a key feature of our rotational mechanism as it allows the surgeon a sense of feel as they navigate the defect space. As such, the distal tip of the shepherd's crook is rotated by a series of translational mechanisms controlled by the surgeon. This design is also able to accept a variety of interchangeable tips and angle curvatures. As you can see, this tip design enables the surgeon to fit the instrument through the defect, elevate the dura off the bone in one location, then rotate to elevate the dura the entire circumference around the defect. Here you can see the cat tongue tip interacting with the pseudo-graft material. As the user pushes forward, the textured protrusions engage and move the material forward. When the user pulls back, the protrusions disengage and the material does not move. Our second concept is a tool with an umbrella-shaped tip that allows for 360-degree elevation of the dura and a pincher-like mechanism to grasp and deliver the graft into the defect. The graft will be placed on the outer side, similar to the fabric of an umbrella. The tool has a slider system to control the opening and closing of the umbrella tip and a button to release the graft material. During the procedure, the umbrella remains closed when being inserted through the bony defect. Once it enters the defect, the user can engage the slider mechanism to open the umbrella, thus separating the dura from the bone and elevating it. Once deployed, a press of the button will release the graft from the pinchers. Now the user can simply slide the umbrella closed and remove the tool from the cavity. The third concept moves away from using the more traditional surgical tool and into an all-in-one tool that elevates the dura and delivers the graft material. The tip of this device includes a metal plate to help initially separate the dura from the bone. Attached to this is a biocompatible or bioresorbable balloon. Extending from that is a hollow tube that delivers the graft material, and at the end there's a lure lock type mechanism where a syringe filled with graft material can lock into the ergonomically shaped handle and deliver the graft. The metal plate will initially separate the dura from the skull and guide the balloon into the correct position. Once in place, the surgeon can use the syringe to begin injecting the graft material. This then inflates the balloon, which elevates the dura away from the skull. Once the balloon is inflated to the desired size, the surgeon can detach the balloon and remove the rest of the device, leaving the balloon and graft in the correct place. Over time, the balloon will biodegrade, leaving behind the solidified graft material. Now, taking a look at the literature, we know a bioresorbable balloon made from PLCL exists, and a brief description of how to make these balloons is easily accessible. While current studies specific to a bioresorbable balloon have focused on regions away from the brain, PLCL has been used in nerve tissue engineering and has also been used to coat neural probes, indicating it's safe to implant near the brain. Here's another look at the three concepts our team has developed to more easily elevate the dura and keep it elevated during transmastoid repair of CSF leaks. This is some of the initial feedback we've been able to obtain from some of our stakeholders. Concept 1 is based off a rotating shepherd's crook profile tip. Surgeons believe this would be very helpful to overcome the ergonomic problem of reaching different angles around the defect. They also like the idea of a textured tip for manipulating grafts, disposable tips, and tactile feedback during rotation. A downside of this concept is that it does not elevate the dura and insert the graft in one. Concept 2 opens up like an umbrella, elevating the dura a full 360 degrees around the defect. The pincher-like mechanisms on the end of the umbrella rods will hold the graft in place as it's being delivered and will release the graft when in the desired position. Surgeons believe this tool could work well in elevating the dura 360 degrees, and they like the slider mechanism, but they are concerned it may tear the dura in older patients. Concept 3 utilizes a bioresorbable balloon to elevate the dura and insert a graft. The surgeons think this is a great idea and believe it would be beneficial to look at materials that can expand in various methods. Overall, our stakeholders believe that we are thinking about this problem well and that we're coming up with concepts that address various key aspects of the need.